Let's proceed into quantum mechanics. Complementarity. The principle of complementarity states that the wave and particle models of either matter or radiation complement each other. It might look something like this. You have a wave, you have a particle, and the wave says, "You are an awesome theory." And the particle says, "No, you're the awesome one." Hence, they complement each other. Neither model can be used exclusively to describe matter or radiation adequately. If you look for one property, you're going to find that. If you look for the other, you're going to find that. The quantum particle is a new model that is the result of the recognition of these two dual behaviors, this dual nature. In other words, these entities have particle and wave characteristics. We must choose one appropriate behavior, particle or wave, that we wish to understand. In order to understand a particular phenomena, we are going to see one or the other. Imagine this. An ideal particle has zero size. Hence, it is localized in space. Here's our ideal particle. It is definitely at some point in space. Whereas an ideal wave has a single frequency and is infinitely long. Hence, it is not localized in space. It is unlocalized in space. It can be found anywhere along that length, infinitely long. A localized entity, though, could be constructed by taking these ideal waves, taking many of them of slightly different frequency, and adding them together, having them constructively interfere, and at some point we are going to end up with a superposition wave packet. So by adding these waves, all of them slightly different, but at some point we end up with constructive interference, we end up with an entity that is constructed from waves but acts like a particle. This is our wave packet. And we've seen something like this in Physics 2 when we were looking at standing waves and in particular beats, when we were adding many frequencies together and we ended up with a beat pattern. So there's two frequencies, one of the beat frequency and one of the superposition of waves. Well, the rate of advance of a single crest in a wave packet is what we call the phase speed. The phase speed is equal to the angular frequency, omega, over the angular wave number, k. And it's strictly associated with one single crest moving along, even within the wave packet itself. While the group speed is the change in the angular frequency with respect to the angular wave number. And as we're looking at it here, it will be represented by the green dots here. So that is the group speed of the wave packet as the wave packet is moving along, the red dot being the phase speed. Well, the group speed actually is the speed of the particle, and it can be expressed in terms of energy and momentum. And if we think of the total energy as being the reduced Planck's constant h bar times the angular frequency omega, and the momentum as being h bar k, then the group speed would be the change in energy with respect to momentum. H bars canceling out top and bottom. And if we express energy in terms of momentum, we would have momentum squared over 2m, take the derivative as a function of momentum of this, and we would get 1 over 2m times 2 times the momentum. If the momentum is mass times velocity, then this is simply equal to the velocity of the particle. So the group speed represents the particle speed. And the group speed of the wave packet then is identical to the speed of the particle that it is modeled to represent. Let's think about probability. If we were to associate probability of a particle like a photon in a region of space, well, the probability per volume would be proportional to the number of photons that we have in that volume at that particular time. And we know that the number of photons per volume in a particular time is in turn proportional to the intensity, how much power we have per area at that particular time. That would be a particle view. If we were to associate a wave view with electromagnetic radiation, we know from chapter 34 that the intensity is proportional to the electric field amplitude E squared. Combining these 2 points of view, the particle view and the wave view, for electromagnetic radiation, we would have that the probability per volume is proportional to the electric field amplitude. So we have a particle view versus a wave view. Electric field amplitude for a particle cannot be associated, but we can associate a different amplitude, the wave amplitude of the particle, which we designate as psi. That squared would be the probability amplitude. In other words, we've associated with the particle a wave function called psi. It's the probability amplitude or wave function of the particle. And the symbol, of course, is indeed psi. This wave function contains within it all the information that can possibly be known about the particle. Although this wave function is associated with this particle, we must caution that the particle is also a function of its environment. In other words, we more properly determine this particle and its wave function as being interacting with its environment. Hence, if its environment has some constraints on the particle, that is included within this function as well. So we think of it as a system wave function rather than a particle wave function. We'll take a mathematical break here and say here are some features of psi that we must accommodate to. It may be a complex function or a real function depending on the system and the potential energy function of the system. It must be defined at all points in space and be single valued. It must be able to be normalized. So if we look at all space, we must be able to find it. It must be continuous in space, which means there must be no discontinuous jumps of this wave function at any particular point in space. These are our mathematical features and constraints on our wave function. But it could be complex. The wave function of a free particle moving freely along the x-axis can be written as a to the negative ikx, and as x approaches infinity, then the wave function would be itself finite. It can be complex in both space and time. Note in this function that I is the square root of a negative 1, so it is an imaginary number. As we expand e to the negative ikx, that is cosine kx minus I sine kx, so it has a real and imaginary part to it. So this wave function has an imaginary part. It's not measurable itself, but if we multiply the wave function by its complex conjugate, and we get, by doing that, we get the probability density, which is the wave function squared. That is always real and positive, and hence that can be measured. Prove that. Complex conjugate. Recall that for a complex number, we would write, say, z is equal to a plus ib. If we found the complex conjugate of this complex number, we would simply write the same number and change I to negative I. So that's our complex conjugate. And this number multiplied by its complex conjugate would be equal to a minus ib times a plus ib, which would be a squared minus ib squared. I squared is a negative 1, so it would be a squared minus minus b squared, which is simply a squared plus b squared. And that would be a real and solvable number. So, if we had a problem in one dimension to find the particle, we would simply try to integrate the probability density in one dimension between 2 points. And that would give us the probability of finding the particle between those 2 points within that interval. So finding the particle between points A and B here would be finding the integration of the probability density between those 2 points. In other words, just finding the area underneath this graph as we're graphing the probability density as a function of x. Well, the particle must be found somewhere. And so if we integrate the probability density from negative infinity to infinity, we must be able to find it. And so the probability of finding it with those limits should be equal to 1, because we'll find it somewhere there. So the probability from negative infinity to infinity of the probability density squared dx is equal to 1. And if we solve this equation, the probability density integrate from negative infinity to infinity, then this process is called normalizing normalizing the function. So we stated that the wave function psi is not itself a measurable quantity at all times. However, measurable quantities of a particle can be derived from the wave function. It is possible to calculate the average position you would expect the particle to be in, and this is called the expectation value of x. We write it, expectation value of x, with these strange brackets around it, and that is defined to be the complex conjugate of the wave function times x times the wave function integrated over all x, negative infinity to infinity. So we put, in essence, we weight the position down by the wave function, and that will give us the expectation value in relation to that wave function. It's a weighted average. We can also find the expectation value of a function of x by doing the same thing. Weight it down by the wave function and put it in between the complex conjugate and the wave function itself. We have to do it this way because it's possible the wave function actually could be an operator. So we might have the operator acting on the function and then integrating over that. So that is the form that we put it in. For example, consider a constrained particle whose wave function looks like this. Psi of x is equal to a e to negative ax squared. This may be graphed as something that looks like this bell curve here, and the wave function is maximum at x equals 0. It kind of drops off on either side as x proceeds as x squared, e to the negative ax squared on either side, asymptotically approaching 0. So it's kind of constrained to remain near x equal to 0. Macroscopic or classical examples of this particular system is the simple harmonic oscillator. A mass on a spring, as it oscillates, is constrained in some sense to be close to a certain value, in other words, the equilibrium position. A ball in this bowl is very similar to that as well. As it rolls up and down the bowl, it's kind of constrained to be located somewhere near that equilibrium position, or like a pendulum on a string. In fact, in these macroscopic systems, they're actually going to spend more time near some amplitude, one place or the other, and they travel fastest through that equilibrium position. So they're actually, in the macroscopic system, they're actually spending more time on the end points rather than in the middle. But when they finally start losing energy, then they kind of stop towards that equilibrium position, and then they're constrained and spend more time there at the middle. So we might think of this QAM example as a simple harmonic oscillator that is in a very low energy state. Possibly, as we'll see later, we're actually in its lowest energy state, and hence it is constrained towards the middle. What is the value of A if this particular wave function is normalized? Well, let's go ahead and normalize it. Here's our wave function, A e to the negative ax squared. And our complex conjugate will also be equal to A e to the negative ax squared because there's no I in this function. Me, myself, and I. So we have our complex conjugate. And if we were to normalize this, we would integrate psi squared dx from negative infinity to infinity and set that equal to 1. This is going to be equal to the complex conjugate times the wave function dx, which will be a negative ax squared times a e to the negative ax squared, which is going to be a squared e to the negative 2ax squared dx, integrate from negative infinity to infinity, and we want to set this equal to 1. Normalizing this then, we have, and let's separate this integral, and so we have 0 to infinity of e to the negative 2ax squared dx plus negative infinity to 0 e to the negative 2ax squared dx. This is the same, we're just separating the integral. Note that if we change the variable in the second integral from x to negative x, what will happen? Well, then we'll have e to the negative 2a negative x squared, and then our dx becomes negative dx. We also, then our negative infinity becomes infinity. So we end up with negative integral from infinity to 0 e to the negative 2ax squared dx. We want to flip the integral now, reversing the order of limits, and that will add a negative sign when we reverse the order of limits. So we have, this is equal to the integral from 0 to infinity e to the negative 2ax squared dx. So that allows us to substitute that in for the second term in this bracket up top. And we now have that a squared integral from 0 to infinity e to the negative 2ax squared dx plus the same 0 to infinity e to the negative 2ax squared dx is equal to 1. So that's going to be 2a squared integral from 0 to infinity e to the negative 2ax squared dx is equal to 1. Bear with me, we're headed somewhere with this. Well, if you look this up in an integral table, the integral from 0 to infinity e to the negative 2ax squared dx is equal to 1/2 square root of pi over 2a. We're going to substitute that in, and we now have, finally, that our normalization is 2a squared 1/2 square root of pi over 2a is equal to 1. Solve this for a. Get rid of a 2 on both sides. Divide through, and we get that a, with a little bit of algebra, is equal to the 4th root of 2a over pi. And hence, our wave function normalized is a, which is 2a over pi to the 1/4 power e to the negative ax squared. Great. That's our wave function. What's the expectation value of x for this particular particle? Well, we now know the wave function. Our expectation value is going to be equal to the integral from negative infinity to infinity of the weighted average of this position. So we have our complex conjugate x wave function dx. complex conjugate is the same as the wave function itself. We could put our a in there since we know what it is now, but let's just leave it as a right now. So we have a squared, integral from negative infinity to infinity, x e to the negative 2a x squared dx. And we want to again separate this on our limits. So we'll have 0 to infinity of x e to the negative 2a x squared dx, and negative infinity of 0 of the same stuff. And again, we're going to make our variable substitution, x to negative x in the second integral. Dx will then become negative dx. And if we do that, then we're going to have this. We'll have a negative x e to the negative 2a negative x squared, negative dx. Negatives cancel out. And we're going to flip our integral again. And that will add a negative sign to that. So now we have a squared positive 0 to infinity x e to the negative 2a x squared dx plus negative same stuff. So they're going to cancel out, and our expectation value then for this is going to equal 0. Just saying that if we look for the particle and on the average, our expectation is that it's going to be found at x equal to 0, right in the middle. So the wave function spends more time about x equals 0, different from the classical simple harmonic oscillator. I've got one around here. I'm looking. I don't. But if I had a pendulum, going like this, tried, it's going to spend more time on the outer edges because it slows down and momentarily stops at the outer edges as it passes through. So that's different from your usual classical simple harmonic oscillator until it loses a lot of energy and is located near its equilibrium point. So at low energy, then they would correspond. So as your n increases, more time tends to be spent at the ends as you increase energy and as you increase your n number, which is what we're going to call our quantum number. But as you get down to the lowest energy state in your classical limits, then the particle is symmetric about 0 and is spending more time near that location. Let's try another example. Let's look at a particle confined to a one-dimensional region of space. In other words, a particle confined to a box. So we have two limits. We have one wall on the left and a wall on the right, and the particle is constrained to move and bounce off these walls. So it bounces back and forth elastically, so it's not losing energy as it's bouncing back and forth between two impenetrable walls separated by distance L. We can actually model this as a potential energy function. Our potential energy function is 0 where the particle is, but it's infinity where the walls are. So the particle cannot make it beyond the walls because the potential it has to overcome there is infinity. So we have this potential well that looks like this, infinite potential well, and that will confine our particle in the box. So inside the box, the potential energy is 0. Outside the box, the potential energy is infinitely large. It can't make it there. And this ensures that the wave function will be 0 outside of the box. Since the walls are impenetrable and there's 0 probability of finding the particle outside the box, we have some constraints here. We're going to say that our wave function is going to be 0 for x less than 0, and our wave function is going to be equal to 0 for x greater than L. Those are limits outside the box. We also should have the wave function is continuous at all points. So if it is 0 outside the box, it should be 0 right at the walls because it cannot be we cannot have any jumps at those points. It must be continuous at those points from the inside to the outside. So we must have that the wave function is 0 at the walls. These are our boundary conditions, and our wave functions that are our system wave functions that include these boundary conditions must be 0 at the walls. So one wave function that corresponds to this idea is a sinusoidal function. The sinusoidal function can be made to be 0 at the walls, and hence our wave function is going to be a sinusoidal function, a sine kx, which will be k being 2 pi over the wavelength. That's going to be a sine 2 pi x over the wavelength. This meets our boundary conditions because when x is equal to 0, our wave function is 0. And note, we also need our wave function to be 0 at x equal to L. So if x were equal to L, that would say that 2 pi L over the wave function would have to be equal to an integral number of pi such that the sine of that will be equal to 0. So we have 2 pi L over the lambda is equal to n times pi, where n is a positive integer, equal to 1, 2, 3, 4, 5, and so forth. So now we have that the length must be equal to a integral number of half wavelengths. If we solve this, pi is being canceled, and n is equal to 1, 2, 3, 4, and so forth. So our wavelength will equal 2 times the length of this divided by n. Kind of looks like a situation that we had in chapter 18 when we had standing waves on a string, and the string was constrained at both ends to be 0. We had nodes at either end, and we had these kind of results for the length of the string and the wave of the standing waves on the string. Applying the DeBroglie wavelength to calculate the momentum, we find that the momentum is actually indeed quantized. Momentum is equal to Planck's constant over the wavelength by the DeBroglie wavelength, and that is Planck's constant, in this case over 2L divided by n. So it's equal to Planck's constant over 2L, which is a constant, times n, which is an integer. So we have discrete values of momentum that will correspond to the wave within these constraints. Since our potential energy is 0, all of our energy in this sense of this wave function is purely kinetic. And our energy then will be equal to our kinetic energy, 1/2 mass times velocity squared. If I substitute in terms of momentum, because it's momentum squared over 2m, we have nh over 2l squared divided by 2m, which is our energy will be equal to h squared over 8 times ml squared times n squared, where n is a positive integer. In other words, our energies will also be quantized. They will be discrete values as we go from one energy level to the next. So we will have quantized energy levels for this particle in a box. For a particle in a box, then, the energy is equal to h squared over 8ml squared, which is a constant, times n squared. Energy levels are going to go up as our integer squared. First energy level with integer 1. The next one with integer 2 will be 4 times that. Next one with integer 3 will be 9 times that. Next one will be 16 times that, and so forth and so on, going as the square of those integers. So our ground state energy actually is going to correspond to n equal to 1. We can't have an energy equal to 0. Lowest allowed energy is n equal to 1. All of our excited states are going to be n squared times that lowest possible energy. Energy equal to 0 is not an allowed state. The particle must exist and it can never possibly be at rest in the quantum state. We see with this example of an interaction of a quantum particle with its environment that if we constrain that particle with one or more boundary conditions, and if the interaction restricts the particle to a finite region of space, this results in the quantization of the energy of the particle, of the system. So, boundary conditions are what leads to quantization, this idea of discrete energies corresponding to that system. How about that? Let's look at an example of microscopic and macroscopic particles in boxes. An electron is confined between two impenetrable walls, 0.2 nanometers apart. Determine the energy levels for the states n equal 1, n equal 2, and n equal 3. Well, we just solved a particle in the box, so the energy for the n equal 1 state would be equal to Planck's constant, 6.626 times 10 minus 34 squared, over 8 times the mass, in this case an electron, 9.11 times 10 minus 31 kilograms, times L, which is 0.2 nanometers, which is 2 times 10 minus 10 meters squared, and our quantum number is n for the ground state, or is 1 for the ground state. That's equal to 1.51 times 10 minus 18 joules, or if I divide this by 1.6 times 10 minus 19, I get 9.42 electron volts. So corresponding that to the energy of electron volts. My next energy level will be equal to n squared times my ground state energy. So my second energy level will be equal to 2 squared times this ground state energy 4 times 9.42, or 37.7 electron volts. And then the next level, n equal 3, will be equal to n squared times the ground state energy, which would be 9 times 9.42, or 84.8 electron volts. Those will be the energy levels for our first three states, 1, 2, and 3. Find the speed of the electron in the n equal 1 state. Well, we're in a box, we're bound, there is no potential energy, so all the energy we have is kinetic energy. Classically, we would say that our kinetic energy is 1/2 the mass times velocity squared. Since our total energy is kinetic, we have in this case our velocity should equal 2 times our ground state energy divided by m square root, 2 times 1.51 times 10 minus 18 joules over the mass of an electron, 9.11 times 10 minus 31 kilograms, all that square root. We are moving at 1.82 times 10 to the 6 meters per second. Pretty fast, just a little bit less than 1/100th the speed of light. So by simply placing the electron in the box, we have it in a lowest energy possible, ground state energy, and we have a minimum speed of 0.6% the speed of light. Let's try a particle in a box scenario with a macroscopic system. A 0.5 kilogram football is confined between two rigid walls of a stadium that can be modeled as a box of length 100 meters. Calculate the minimum speed of the football. Well, we're going to calculate the ground state energy for n equal 1 for this macroscopic system, and that should be equal to Planck's constant squared over 8 times the mass of the football, 0.5 kilograms, over the length of our box, which is 100 meters, square that, n is equal to 1 for our ground state, and this would be equal to 1.10 times 10 to the minus 71 joules, or I think I just leave it like that. So the velocity associated with this much energy if all of our energy is kinetic, is 2 times this energy over the mass, 2 times 1.1 times 10 minus 71 over 0.5 kilograms square root, or 6.63 times 10 to the minus 36 meters per second. That's the minimum speed of the football, and if the football had that kind of speed, you wouldn't be able to notice it. 10 to the minus 36 is far beyond any capable measuring and any capable visual cue that you might be able to pick up on the football. So as far as we're concerned, it would simply look like it's at rest. This is definitely too small to be measurable by the human eye. That concludes this first lecture, but I just want to look at this picture, this very interesting picture. I think it's a Nobel conference in 1920s, probably 1927, and there are a lot of important people in this picture. We can recognize Henri Lorentz, who won the Nobel Prize in 1902. Madame Curie won the Nobel Prize in 1903, a beautiful woman. You can see here that she is quite ravaged by the effects of radiation at that point. This guy always was talking about himself. That's Bragg. 1915, he won the Nobel Prize. Max Planck, 1918, for quantum nature. Albert Einstein right there in front, 1921. We have Niels Bohr, 1922. Compton, 1927, sharing it with Reese Wilson. There's Richardson, 1928. DeBroglie for matter waves, 1929. We have Heisenberg, the uncertainty principle, 1932. A lot of gold accumulating here in terms of Nobel Prize. We have Schrödinger and Dirac, responsible for the wave mechanics theory. 1933. Who else? We have Pauli, famous for the Pauli exclusion principle. 1945. So a lot of famous people here. I almost forgot. 2013, we have Golben here, responsible for getting the Nobel Prize for the effects of too much gold on a small group of people. That is a measurable effect, and he got the Nobel Prize for measuring that. So, great conference, great picture, a lot of Nobel Prizes involved with this picture. Let's go on to more quantum mechanics.